Namaskar. It gives me immense pleasure to introduce you to the Indian Plumbing Association's Plum Talk series. As part of Plum Talk, plumbing industry experts from across the country will be explaining the nuances of plumbing technology in an easy and understandable manner. And this will make plumbing science easier for building industry professionals, engineering and architectural students, as well as the general public to understand the basics of plumbing technology. Let me give you a little background on IPA, which is the apex body of plumbing professionals in India. IPA is now a 29-year-old body started in 1993, currently has 24 chapters working towards redefining plumbing standards in India, tirelessly working towards better plumbing for a healthy living. I therefore request you to please go through the Plum Talk series, which will be a guide for students, for architectural students, for even current architects and engineers, so that you are able to improve your knowledge on plumbing and ensure that all plumbing installations are installed not only as per codes, but we make sure that whatever water we use, we move towards net zero water and net zero sanitary waste.
Hello friends, today I am sharing with you something which has become part of our life. It seems simple, but actually it is full of complexities in terms of technicalities. I am talking of plumbing. History tells that many civilizations developed and flourished on the river banks of Indus, the Nile, the Tigris have been the cradles of some of the greatest civilizations of this world. The rivers acted as a reliable source of water for agriculture and other personal human needs. Increase in population resulted in migration to areas away from river banks, slowly leading to urbanization. But still, natural resources in terms of inland water bodies and forest cover were available near the human settlements, where people were able to satisfy their needs for water and answering calls of nature away from their habitable spaces. Further growth led to the provision of water sources like wells near homes, and also came on the scene dry privies. And then came the growth of organized industry sector globally, spurred by industrial revolution in Europe, leading to urban overcrowding, and an increase in diseases attributed to the prevailing insanitary conditions. Also, it led to emergence of an economically affluent class which demanded better sanitation provisions within the homes and places of work. Such community health related as well as aspirational living styles demands started the installation of plumbing systems for supply of water and collection and conveyance of used water within the buildings. What would have been started as a need-based installation over a period of time, it got transformed into practices which were mostly based on past experience and codified guidance. But with the buildings becoming taller and more complex, need for better understanding of fundamental operational characteristics of plumbing systems got felt, and the researchers started the systematic investigation of building drainage systems operation and understanding of the underlying fluid mechanics. In this episode of Plum Talk series, today I will delve into chapter 5, Soil and Waste Drainage, from the book A Guide to Good Plumbing Practices. It's a publication of Indian Plumbing Association. I will try to explain the basic fundamentals of building a drainage system, which is also called the above ground drainage system. The role of a modern building drainage system is to transport fluid, fecal and other waste from appliances to the sewer outside without any leakages, spillages, interruptions, and most importantly, with no possibility of cross contamination. What is exactly meant by cross contamination? Cross contamination is the ingress of foul and potentially health hazardous air from the drainage network into the habitable spaces. As in other construction related trades, in plumbing also, over a period of time, different practices and methods of installing piping systems got developed. Talking specially about drainage piping systems, these development and practices were mostly related to the way the used water was conveyed and finally disposed of. The used water discharge from water closets and urinals had been termed as black water, and the less obnoxious discharges from bathing areas, wash basins, kitchen sinks, dish and cloth washing operations, etc. got termed as grey water. Black water, being perceived as extremely unpleasant, a separate system for its collection, conveyance and disposal got conceived. For disposal of black water, the primitive treatment systems like soak pits, leach pits, cesspools, septic tanks, etc. got evolved, wherein the water and the solids were separated. Water is to percolate into the soil, while the solids are retained in a covered pit. The major part of the collected solids get converted into gases and water over a period of time by the bacterial mass using it as a food. Gases escape to the atmosphere, water gets absorbed into the soil, and the residual, also called sludge, mainly consisting of undigested or inert solids, and the active bacterial mass is removed periodically from the pits and used as manure for horticulture purposes. On the other hand, the grey water, being considered as less offensive to our senses, was conveyed separately and usually discharged into stormwater drainage system, finally finding its way into the water bodies like ponds, lakes, rivers, etc. These primitive methods of disposing of black water and grey water separately led to the practice of installing two separate pipes for conveyance of used water, one for black water called soil pipe and another for grey water called waste pipe. As these pipe stacks are terminated above the rooftops and hence connected with the atmosphere, are also called soil and vent pipe and waste and vent pipe respectively. This type of practice of installing above ground drainage system got termed as two pipe system. Many a time there is a third pipe stack called vent pipe in such installations, which has branches connected to soil and waste stacks at intermediate levels. In some old buildings of the Victorian era, you may find two such vent pipes, one connected with soil stack and another connected with the waste stack. We will be shortly discussing in this episode the purpose of this vent pipe. The practice of two pipe systems along with a separate vent pipe started proving uneconomical for high-rise buildings as it requires more space and consumes more material and other resources. This led to the development of more economical but still safe and efficient above ground drainage systems. The use of detergents, cosmetics, and other chemical-laden edible and non-edible products of daily use has made the grey water a potential pollutant for water bodies. The economic reasons, the research efforts, and understanding of the fact that the grey water being perceived as less obnoxious is actually not that clean led to the introduction of one pipe system. In this system, both soil and waste branch pipes bring used water from sanitary fixtures and other appliances, connect with the same pipe stack called soil, waste and vent pipe. There may be an additional vent stack in the system also. Over a period of time, the one pipe system of above ground drainage has become popular and has found acceptance for high-rise buildings. Development of above ground drainage system did not stop with acceptance of one pipe system. Researchers started questioning the need for a separate vent pipe. Also, the environment sustainability movements started advocating the lesser consumption of material and resources. This led to the development of the single stack system. In the single stack system, pipe stacks are actually sized to carry solids, liquid, and the air with minimal venting requirements. The additional vent stack is dispensed with. The air forms the central core of the discharge flowing down the stack. There is no doubt that single stack system takes less space and require relatively less materials, but it may require larger diameter stacks. Also, the system has certain restrictions like limitation on length of branch, soil and waste pipes connected to stacks, minimum distance between soil and waste branch connections onto the stack. For a very high-rise structure, the single stack system may require special or proprietary fittings and appurtenances. The purpose of these proprietary fittings is to facilitate the discharge of liquid waste from branch pipes into the stack without disturbing the movement of central air core in the stack, and also facilitate entry of air into the stacks at intermediate levels so as to neutralize occurrences of positive and negative pressures within the drainage system. We will be shortly discussing more about some of such special fittings in this episode. For an effective and efficient drainage system, apart from pipes and fittings, there are two more very essential and important constituents. One is a contraption called trap and another is a system called venting. For better understanding what exactly these are, please look at the images. The word trap, as referred in the plumbing jargon, means a U-tube shaped contraption filled with water. On one side of U, a sanitary appliance or a drain point is connected, and on other side is the drain pipe. This water within U-shaped contraption prevents the cross-contamination of habitable spaces from the drainage network. In simple words, this means the foul and dangerous gases from the drainage system cannot enter habitable areas of any building because of the two water columns in the U act as seal or barrier. Interestingly, the history of the plumbing as we design, install and use today can be traced back to as early as 1775 when a Scottish mechanic Alexander Cummins invented the water seal trap. Surprisingly, Alexander Cummins was a mathematician and a watchmaker too. He is credited with inventions of many other instruments also. Now coming back to the main context, we move further to know more about traps. There are two types of traps, integral and external. Integral traps are part of the sanitary fixtures like in water closets and in modern days urinal bowls. External traps are installed between drain outlets of sanitary fixtures and other appliances requiring drainage connection and the drainage pipe. A trap is designated by the diameter of its outlet and the depth of water seal it has. The depth of water seal denotes the maximum fall in water level in the trap beyond which any further fall will make the trap useless, as that would create a passage for foul gases from drainage network to enter the habitable spaces. The other important attributes of traps shall be self-cleansing design, meaning its construction shall be such that solid particles in the wastewater pass through the water passage and do not settle at the bottom of the trap. Another aspect of trap is its diameter shall in no case be smaller than the diameter of outlet of the sanitary fixture or appliance to which it is connected. Trap shall also have uniform bore and its construction shall not be dependent on internal partitions or other sliding parts for retention of water seal. The soil and waste drainage system shall be fully ventilated to allow for escape of foul gases and to let in air from the atmosphere to maintain the equilibrium in the drainage system. The occurrences of positive and negative pressures within the drainage system causes siphonage and blow-offs respectively, resulting in loss of water seal, which leads to the entry of foul and dangerous gases into the living quarters. Sizing and the alignment of the installation of vents play a very important role in maintaining the atmospheric pressure within the gravity drainage pipes. Vents are normally terminated above the highest entry point of the vertical or horizontal drainage system. The terminal point is open to the atmosphere but protected from top with a cowl. This terminal point allows the inflow of air at atmospheric pressure into the drainage pipework, which in turn neutralizes the negative pressure. Similarly, the positive pressure induced air also escapes from the vent system rather than exerting pressure on the water seal of the traps. In situations where horizontal branch drains run full before getting connected to the stack, the discharge into the stack creates sufficient momentum due to the development of negative pressure at the entry point of stack, and this results in water seal in the trap getting carried away with the discharge. This phenomena is called self-siphonage of the trap seals. The downward movement of mass in the stack may create negative pressure upstream if the space created by the downflowing mass is not taken over by sufficient air quantity. Such situations may result in water in the trap seals gushing to the negative pressure zone. This phenomena of losing seal in the trap is called induced siphonage. Once the liquid wastewater traveling in the pipe stacks reach the ground, it's need to change the pattern of flow from vertical to horizontal. As you know, any change in direction, whether walking or driving on the roads, or even in our personal life, requires extra attention. Same holds good for the liquid waste also. In pipe stacks, the liquid waste moves down because of gravitational pull, but it's still subjected to resistance offered by the inner wall surfaces of the pipe stack. Also, this flow is usually depending upon how many branches are discharging simultaneously into the stack, and that too at what levels in the stack. The discharge moves down at a relatively higher velocity, also called terminal velocity. Once it hits the ground level or bottom of the stack and changing the form of flow to horizontal direction and slowly comes to a steady state after traveling a certain distance depending upon the slope in the horizontal train. This transition from vertical to horizontal direction releases the energy gained by the flowing mass during vertical travel, resulting in a hydraulic jump. This hydraulic jump reduces the passage for the escape of air traveling down with the liquid to the horizontal train. The entrapped air at the bottom of the stack generates a positive pressure in the piping system. This positive pressure can get developed to a magnitude capable of blowing off the water seal of the sanitary fixtures connected to the stack at lower floors. Hence, in high-rise buildings, it is not recommended to connect branches from the lower floors closer to the stack bottom directly to the stack. Many a time you come across situations where it is not possible to provide ventilation to the drainage system, or in other words, it is not possible to terminate the vent in the open. For example, if the terrace of a building is to be used regularly for functions or any other activity involving movement of many people, and also there are restrictions on the height of the structures or features or objects which can come above the terrace level. Because of people's movement, the vent cannot be terminated at below human height, and because of height restrictions, it cannot be taken up to a height which is safe from health and odor nuisance point of view. For example, a building has a sloping roof, but from an architectural aesthetic point of view, vent pipes cannot be terminated above the sloping roof level. The termination of drainage vent pipes at appropriate levels and positions become a challenge. For such situations, now special appurtenances are available which perform the functions of vent pipe systems but need not to be terminated in the open. One such appurtenance is air admittance valve. When installed at the stack's highest point or a branch drain's highest point, let the air inside the pipework in situations when negative pressure develops inside the drainage pipework. Have a look at these two images where the use of this special purpose appurtenances has been shown. One in the vertical stack pipe, another at the end of the horizontal pipe. In normal situations, its apertures remain shut and do not allow the foul gases to escape to the surroundings. There is another very interesting appurtenances called positive air pressure attenuator, PAPA. Have a look at this fitting, how it has been installed in a stack. This absorbs the positive pressures developed in the drainage system. This helps in preventing the loss of water seal in traps due to blow-offs. However, these appurtenances find limited acceptance because of cost factor, availability being not so easy, and the design and application criteria still being kept under wrap of secrecy by the manufacturers. So far, what I have talked about traps and venting is a simplified purpose of these two very important constituents of soil and waste drainage system. In the drainage systems of high-rise buildings, venting and traps play a much more complex role. Actually, the flow of wastewater in the above ground drainage system is unsteady. It varies from empty stack to one or more branches connections discharging simultaneously. This results in varying amounts of air present in this stack to get entrained in moving down mass, creating air pressure transients within the drainage network. A properly designed venting system is required to take care of these air pressure transients. If not handled efficiently, the air pressure transients can deplete trap seals. For deeper insight into this complex mechanism, it is necessary to understand the basics of above ground drainage system and venting systems in terms of their fundamental operational characteristics and also study the principles of fluid mechanics. Armed with this accumulated knowledge and after using simulation techniques, better designs and products can be produced. Ultimately, this can lead to the development of drainage systems which require less water to transport the solids, provide better efficiency and reliability in preventing cross connections between habitable spaces and the drainage networks, resulting in better hygiene and health of the communities, and the most importantly, reduce the carbon footprint of buildings by consuming lesser resources. We'll take up the topic of these complexities involved and other related issues in one of our Plum Talk series in future. I, Mukesh Asija, now take your leave, and before leaving, I want to tell you that I love Indian Plumbing Association for its mission, redefining plumbing standards.